while Yali sets up, let me just do a little bit of introduction. So there's lots of goals for us for a day like today. One is to bring amazing people to come and share their knowledge about game development and the games industry. Another is for a chance for us to show you some of the things that we get up to at King's in the Department of Informatics, but also the rest of the university as well. That's what the festival's all about. And so I'm really delighted to have today one of my colleagues, Yali, who is a machine learning researcher and an expert in collaboration with humans. And you're going to be talking about some of your research in that area. Are you okay with the lapel, or do you prefer the handheld?
Hello, can you hear me?
Oh, that sounds good.
Okay.
Yeah, fantastic. Okay, I'll let you take it away, Yali, then.
Okay, great. Oh, we just want to check, is the pointer working? Can it point or?
The pointer, it is working, but it's a bit faint.
Okay, that's fine.
Yeah.
Okay, great. Hi, good morning, everyone. Thank you for coming to this AI Festival today. My name is Yali Du, and thanks Mike to the actual nice introduction. And actually, in the previous talk, Mark Hammond has given a very interesting and a nice introduction about the game AI. So how to use AI to design games. But the thing that I'm going to talk about is just on the reverse. So how to use AI to play games. So we have some pre-designed games, and the games are here, and how we could train the AI agent to play the games. And so this would be like, so the title today include like how to play games with human and how to learn with human to play. So basically, it's like two different things. So one thing is that so basically, for example, for some kind of games, multiplayer games like a game of chess or Go. So sometimes it's like it's a competitive game, but for some kind of other cooperative games like Overcooked, maybe some of you might have played that. It's a game from Nintendo. So it's like a two-player game. So it's like how could you enable an AI agent to be able to partner with any humans, or on the other hand, also like this will be the one thing. And another thing is that sometimes, so can we learn from human to play some games instead of like ask this agent to learn from to learn itself? We'll start from a little bit background of this, a little bit background of the progress in AI. So in the past few years, I think many of you might have heard about or have been kind of involved in some kind of the evolution of AI. So basically, in the past years, we have witnessed the great success of reinforcement learning. So the reinforcement learning is kind of a new learning paradigm. It's different from a typical machine learning framework like supervised learning. So in the prior to the reinforcement learning, so many machine learning problems are just about having a static data set where we have some fixed input and a fixed output, and we want to learn some kind of machine learning models that could fit the pattern to fit the pattern in the data set, so then just predict the output based on the given input features. But for the reinforcement learning, the difference is that there's no such kind of like data set. It is learning from the interaction with the environment or with the task that's given. So for example, like the game of chess or the game of Go or the game of StarCraft 2. So basically, this this is actually reinforcement learning. It's kind of very close to how humans learn things. We learn from like the interaction of the games. So when we learn to play StarCraft 2 or we learn to play Super Mario games, and we take some actions, and and this gives us the positive rewards, and we know that, okay, it's good action, and we could repeat that. But if we take some actions, like for example, in Super Mario, if you touch some like poisonous mushroom, you will be dead, and you know that it's a bad action. You will avoid taking it again. So for the reinforcement learning, it's just this kind of it's just this kind of interactive decision-making loop. So it interacts with the environment and it collects more data. But okay, well, this is good action, that is bad action, and it updates in knowledge. So update its way, its policy of playing this game. And so basically, in the past years, I think we have heard about many like interesting products like AlphaGo, AlphaStar, and also like OpenAI, the .5. It's actually a multiplayer game. So 5 players play against another 5 players in the enemy team. So it's like actually this would be the problem of multi-agent reinforcement learning, which requires collaboration among the agents. And especially recently, people talking a lot about the ChatGPT. So for ChatGPT, it's kind of conversational robots, and basically they have also used the reinforcement learning. So they have also used reinforcement learning in training their agents to be able to align with human values. So, but actually for the existing success of this kind of games like AlphaGo or AlphaStar. So one thing that we have noticed that is actually this kind of the training of this kind of reinforcement learning agent to play in the game of chess or Go has relied on the well-specified reward functions, which is actually designed by the game designers like Mark Harmon. So basically, based on this kind of well-specified reward functions, we could train the RL agent to play the Go that can defeat human champions or play the StarCraft 2. However, so for this kind of decision-making tasks, usually this kind of reward functions does not come with no price. It comes with cost. So basically, on the one hand, this kind of so we wanted to train this agent to do some tasks like, for example, for the games, it's like okay, just for the games, just defeat the enemies. But for some kind of tasks like the robot arm, controlling the robots to pick up some stuff or to deliver something for you. So for this kind of tasks, it's like all the decision-making tasks. So for many of these cases, on the one hand, the quality of the reward function would be kind of highly dependent on the game designer's understanding of the task. So the game designers understand the task better, and they could design better reward functions that could represent what this agent needs to do to achieve higher rewards to achieve the task. But so basically, this would also rely on some kind of experts knowledge of how this tasks works. So for example, if you're training using reinforcement learning to train a kind of a delivery robot, so how to design the reward function, and on the other hand, this reward function in some cases can be difficult to specify. So for example, so if you're building a kind of a recommender system that is aiming to maximize the customer's satisfaction, so the customer satisfaction could be something that's not easy to specify, or it's not even possible to be specified. So in that case, that's kind of because it's actually subjective. It's depending on different people's preference. So the question that we want to ask here is that how could we train the reinforcement learning agent for this kind of the interactive decision-making tasks without a reward function? So without a reward function, could we? It's like if you're playing Super Mario, you're playing Super Mario, there's no kind of reward signals telling you that okay, you're getting higher reported rewards because you collect some golden coins. If there's no such kind of reward signals, how could we train an agent to play this game well? So our answer to this question would be learning from humans. So learning from human feedback, and I will get into that point later. And so here is just some kind of overview of the projects that our group is working on. So basically, our group work on the projects on like enabling the agent or enabling the machines or AI agent to be able to exhibit cooperative and trustworthy behaviors. So cooperative is like multi-agent scenarios where you have some games like robot multi-robot control to collaborate to pick up some stuff or to work in the manufacturing. And to responsible behaviors, that's like in the cases we want the robot to be safe, and we want this agent to conduct safe and responsible behaviors. It's like, for example, in the conversational robots, we don't want this agent to kind of generate some hateful comments. We want this agent, this chatbot, to be kind of peaceful, kind, and aligned with our kind of common understanding of moral values. And in this end, actually, we have worked on like a lot of different topics. So here are like several video demos. So it's a StarCraft 2. So it's StarCraft 2 mini games, and it's a robot arm control. And this is Overcooked games, and the other is like traffic control. So these are kind of testing bed or the testing tasks for our algorithm. And for the questions that we ask, for example, in the multi-agent learning, so how could we enable the agent to collaborate? And also for multi-agent tasks, for example, in the game of soccer, so we have multiple agents, but only one single reward. How could we kind of fairly assign the credits to different agents so that each agent would be happy about their contributions to the team's benefit, and the communication task as well. And on the right hand side, that's the evaluation part. So we have this kind of AI agent that's designed to play this game, but how good is its performance? How good or how bad is it performing? So this can be straightforward in some cases if you have pretty clear reward signals, but sometimes, for example, in the rock paper scissors, or in this kind of two-player competitive games, like a game of Go, so one agent's performance is evaluated solely based on the results of its competition, of its match with the other players. So if the other players is a very strong player, and you will always win, you will always lose. If the other player is a very kind of bad player, you will always win. But actually, does that mean your performance is kind of changing? Actually, it's the same. So basically, it's like how to fairly evaluate the agent performance. And in the middle part, it's about the reinforcement learning, human in the loop reinforcement learning. This would be the major content that I'm going to talk about afterwards. So for this part, the question that we're asking is, if we get the human involved, can we achieve the reinforcement learning for the higher efficiency, or for the safety concerns, to avoid the safety concerns between the safe agents? And so the major content talk would be focused on like the agent alignment, the control part. And let's get back to the problem of learning with humans, learning to play with humans. So this is actually the roadmap from OpenAI about how they train their agent, how they train the ChatGPT. So basically, it's divided into kind of 3 stages. And in the first stage, it's just so they get a lot of offline data. They collected a lot of data from the internet and from different sources, and they do the pre-training. So it's kind of the supervised learning part. You supervised learning side. So basically, give the input, and they feed the model to generate the output from the data set. And in the second part, so actually they spend a lot of time, like a year to tune their model to be kind of more aligned with humans' values, to be able to generate to be able to avoid generating hateful comments, to be able to behave morally that's aligned with humans' values. So in this side, how to define the morality of an agent? It's actually a difficult problem. So it's hard to define this kind of reward signals. And in this case, what they have used is the learning from the humans' feedback to achieve this goal. So this is also what we're going to talk about. So what they have done is that, ask this agent. So basically, when you take the conversations with the agent, ask this agent to generate different answers, different responses. So if you have used the ChatGPT, you might know that. So if you ask it to regenerate every time, it would generate something different. So ask this agent to generate different comments. For example, you ask him a question, and it will generate like different responses, like A, B, C, D, and then how human get involved. So in this case, human would be involved to kind of rank these comments, rank these kind of agents generated comments. So the human thinks that, okay, A is better than B. So based on this kind of human preference, we could kind of, again, perform some kind of machine learning to recover a reward model, that would label the rewards for this kind of, label the rewards for these different comments, and then this would help, and then we have a recovered reward model, and this reward model could be used later on to train the reinforcement learning agent. And in the stage two, what they have done is just recover the reward model from the human's preference. And in the stage three, so based on the reward model, they again fine-tune their chatbot, fine-tune their agent. And so the PPO model here is just one popular standard benchmark in reinforcement learning. It's proximal policy optimization in the typical reinforcement learning agent. So this would be kind of our work. The work that we'll talk about later is also aligned with this kind of roadmap. So for the reinforcement learning, we have an agent and an environment. So it's like we have two important elements in this kind of typical reinforcement learning task. And for the environment, that would be actually just, for example, just be some games. So there'll be the game called maybe, for example, Super Mario. So the environment is just a game, Super Mario, the game engine. And we have an agent, and this agent could take some actions. For example, this agent chooses to move left, move right, or go ahead, and this environment would receive this action, and the environment would kind of undergo some kind of state transitions. So the environment, and that environment would tell the agent what your next state would be. So for example, the agent currently is at this location, and they choose to do action of moving forward, and the environment will tell this agent that, okay, your current location would be here, and this is environment transition, and this environment is also telling this agent what reward you will get. So for example, you get a positive reward or negative reward, and this agent is using this kind of its own policy that we just usually parameterize as policy pi theta to generate this kind of actions. And this policy pi is kind of, so basically currently we are usually using the deep learning to tackle the large scale reinforcement learning problems. So basically we call that deep reinforcement learning, because for the agent policy pi, it's just represented by a deep neural network. And for the agent, its objective is to maximize the accumulated rewards. So it's not a kind of only maximize the immediate reward, immediate response. It's also it's also trying to take the actions that would lead to higher rewards in the end. And so that's the previous slide showed the typical framework for the reinforcement learning. And for this framework, it's a reinforcement learning from human feedback. This is about how to learn from humans to play the games. So in this part, actually, if we look at this framework, the only difference is that so the environment is no longer generate reward signals for our algorithm. So our algorithm is not receiving the reward signal from the environment. And on the other hand, this reward signal would come from a reward predictor, that's kind of aligned with the human's feedback. So this would be the typical kind of difference to the standard reinforcement learning framework. And this is usually called the reinforcement learning from human feedback, RHF. And so an example is like this. So for example, if you are training a biped robot to learn to walk, and and the RL agent would generate different trajectories. So the upper row and the lower row, so it's like two trajectories generated by this RL agent. And we ask a human to see which one you prefer, and the human would say that, okay, we prefer this one, so because this is like more balanced, and then we no longer need the reward signals. We no longer need the reward signals from the environment, but based on the human's preference, we could try to kind of reconstruct some kind of reward predictors. And actually so far this would be the first this would be the first and foremost take-home message. So basically, this is that for training a reinforcement learning agent, you no longer you don't always need a reward signal to train a reinforcement learning agent. You could use human's feedback or this kind of binary preference labels. That's much easier to be obtained That's much easier to obtain compared to some kind of reward signals. So it's like, for example, if you ask a recommender system to recommend something recommend some kind of fruit that you would like to eat today. So the recommender system might be find like it very difficult. But actually if you kind of tell that, okay, comparing the apple and the banana, you would prefer apple, or comparing the banana and something else, you would prefer one of that. So this kind of signals would be much easier to be obtained from a human instead of a well-specified reward signals of okay, apple would get a score of 5, and a banana would get a score of 3 or something like that. So next, I'm just going to talk about some work that we have done to improve the efficiency of the feedback. Because the first message is that actually human feedback is useful. It can be used to replace reward signals. And the second feedback is that so how could we improve the feedback efficiency? Because also with human feedback, we also want to use as less human feedback as possible, because it's also costly to ask humans to sit here to tick, okay, I prefer this one compared to that one. And so basically, the next part would be a little bit on the technical side of how we did that, how we designed algorithm to improve the feedback efficiency for RL agent. And so the motivation for this work is that so feedback data can be extensive, and the previous works. So these are some kind of reinforcement learning curves of how they performs with how they performs under different number of feedbacks. And here the people is actually one important baseline algorithm, and it requires 25,000 to 50,000 of feedbacks, or to this kind of 20,000 to 50,000 of binary labels, and then it recovers the reward model, and it could kind of learn some useful performance for this drawer open task. So as you remember, this like a robot open the drawer. So for this task, and this could be some kind of we think it can be reduced. So what we have observed is that if we have less human feedback. For example, if we only have from 50,000 to 1,000, if we only have 1,000 kind of this kind of binary labels, and this would be less data, and then based on this less data, we would train the reward predictors, and it might lead to a less accurate reward predictor. And in the reinforcement learning part, and usually we would need a reward kind of a critic function like Q function to evaluate how good or how bad an action is. And so in this case, this would lead to some kind of problem of confirmation bias. So we have less sufficient data, and we train a inaccurate reward function, and then based on inaccurate reward function, and we train actually inaccurate Q function or state or action value function that provide inaccurate evaluation of the agent's actions. So from here, and motivated by this, we just kind of slightly changed the learning objective for the preference-based RL and leads to, and we just generate an algorithm that is much more feedback efficient. And so here, so this slide just shows the this slide shows the standard framework for the preference-based RL. So basically, for the preference-based RL, so we have we don't have a ground truth reward function, but what we have is we have two trajectories. So let's note that at sigma 0 and sigma 1, so it's like a trajectory that I showed that before. So like a biped robot, it learns to run in a balanced way or just it learn to fall down. So sigma 0 and sigma 1, and then it's kind of a trajectory with, for example, 10 time steps. And for the different 10 time steps, we accumulate the reward for this trajectory. And based on this kind of R hat phi, so R hat phi is the reward predictor that we don't know, and we try to learn that. We try to inference this from the preference data that we have. And so basically, this is actually a binary prediction model. So binary prediction model. So based on the human preference says that, okay, I prefer this one, I prefer A comparing to B. And the predictor, P phi, is just predicting that, okay, A and B, which is better. And so basically, this loss function is just enforcing this predictor to be aligned with human preference. And so that we could use like we could update this by like propagation and update this R hat phi, the reward function, so that based on this reward function, we have this predictor that could generate the preference labels that's aligned with humans' ground truth label. So this would be kind of the standard framework from existing work. And then based on the reward signal, we just train the RL algorithms. And so this is for our paper, for our work. So what's the difference here is actually the first equation here. So how we construct this preference predictor. So we do not use the reward function R hat, but use the Q function directly. So the motivation here is that basically because the reward function, as we mentioned, if we have less data, and it will be inaccurate, and the inaccurate reward function leads to inaccurate Q function. Because so Q function is the action value is evaluating the action's long-term return, and reward function is evaluating its immediate return. So for the Q function, it's actually just a discounted sum of the agent's action value in the long term. And so by using this Q function directly, actually we just skipped one step in one step of evaluating Q from reward function, and in that way we could kind of eliminate the problem of confirmation bias. And here, based on the Q function, the evaluation of the trajectory, the evaluation of the performance trajectory, we still use the same kind of binary classification loss, and then so basically here we just constructed a bi-level programming objective. So in the inner loop, we just learn this Q function. So learn this Q function. This is typical standard Q learning. So we try to feed Q theta, parameter by theta, to this target, and actually to estimating this Q function, it relies on the alpha hat. It's alpha hat. That's the reward function. And basically we don't have an explicit gradient to that. We use the implicit gradient, and so basically it's a kind of bi-level programming. And so for the inner loop, it's a standard. So this is about the optimization side. For the inner loop, it's a standard standard Q learning loss. So standard Q learning loss, the mean square error, and do the update. And for the outer loop, we first need to find the gradient for the reward function R hat phi, and we first find the gradient to the first find the gradient to the parameter theta. Theta is the parameter for the Q function, and then in updating the theta, because here we see that theta is relying on the r hat, so we'll find the gradient of r hat. So it's a little bit kind of a twist of the chain rule of derivatives, and also for this algorithm, also have the convergence guarantee of this algorithm. So the inner loop and outer loop, so the Q function would converge to the local minimum in this case. And so basically, that's also not very important. So it's just a little bit kind of technical side. And so for the experiments, we have used this framework we have tested this framework in this kind of robot control tasks. So we want to control these robots. We want to control this kind of robots to learn to use a hammer, or to learn to open the door, or to press the button, and from this kind of human preference data. And then here are some kind of experiment results. So experiment results here. So the blue line in the top, actually this is the algorithm that have used the ground truth reward signals. So basically here you see that it performs best because it's using the more information raw signals. But for our algorithm, so it's a purple line here, comparing to the baselines, we should see that so for this purple lines, it learns faster. So it kind of converge with. It kind of learn faster, so with less environment steps. So basically here, so the y-axis is success rate, and x-axis is the environment steps, or the number of steps that this agent need to interact with the environments. So basically, so in the reinforcement learning training, we usually measure this kind of number of environment steps, because we also want this agent to interact with the environment as less as possible for that be the sample efficiency purpose. So here we see that this, in general, this purple line, so it performs better, like learns faster and learns better in different tasks. And here would be just some demos. Some demos that's generated by this So this is some demos. So the algorithms that control these robots is all like is all the our agent PyC that's learned by our algorithm. And so this would be the everything about this work. And so another thing that I would like to briefly mention is one is about the human in the loop CFRL. So basically, we could use the humans to provide feedback to the agent behavior to correct its behavior to be like more safe. So this is some kind of proof of concept results that we have conducted. So to train this robot to navigate to the target location, there will be some dangerous areas like water, and we just do some. So our results shows that with human preference. So actually, with human preference, this agent learns to converge to a safe policy to navigate to target location with actually around 5 episodes. But with Q-learning, it uses the reward signals. It takes around like 25 episodes to converge to a safe policy. So it's a kind of indication that human preference sometimes can be even better than the reward signals. And the last piece of information I'll mention is about this game. So it's Overcooked. It's a human AI coordination. So actually, in this kind of two videos, these two videos, the agent in green hat is controlled by AI, by our algorithm, and the agents in blue hat are controlled by the humans. So basically, this is a human AI coordination task. So they are coordinating together to cook this, for example, this onion soup. So they collaborate to put the onion in a pot and cook that for 20 minutes, and then put that in plate and serve to the customers. And so what for this work, the kind of for the technical side is just ask this AI agent to be trained with a diverse, different style of partners in the training stage. And then in the testing stage, it will be able to kind of recognize different style of human players and collaborate with human players. So it's this will be the last piece of work. And so in summary, we have two messages. The first is that human preference plays an important role in the scenarios where the raw signals can be not available, or can be like it can be even better. It can be even better than raw signals sometimes. And second thing is about human AI teaming. So human AI teaming, human AI coordination, it had kind of currently kind of attracted some attention for the tasks like this kind of cooking games, very easy cooking games. But it has many potentials, like for example, human-robot coordination, which has not yet been explored fully yet. And so for next steps, and so there's like also a lot of open questions along these lines, like how to further improve the efficiency of the feedbacks, and how to kind of and how to address maybe some kind of conflicts among the humans. So you ask humans to labels, and these humans might have conflict values, and the generalizations to new tasks, like and also like grounding to more kind of physical applications like robot control tasks. That'll be all for my talk. Thank you all.
Sorry, I may just have to project because
Sorry, I think I just run
one button. It's not hard to switch these on, but somehow I did still forget. Thank you so much, Yali, for that talk. Yali and I are hoping to collaborate and get some more machine learning agents playing games. And I also wanted to say that in a minute, we're going to go for a coffee break outside to the exhibition space. And there's a poster and some more videos of Yali's work in the exhibition space as well. So when you're grabbing a cup of coffee, you can check that out. And if you're around London on the 7th of June, Yali will be giving a live demo. Will you be there in person for that?
Yes, I'll be here.
Great, yeah. So you can come and actually play the Overcooked demos with the AI and learn a bit more about how it works. Do we have any questions from the audience before we go for coffee? Yes.
I have a question about reward calculation, especially with human input. So have you considered actually using more advanced LLM models like GPT-4 to do the labeling for you? So the context is like if we have a lot of people, or if we need a lot of human to do the work, then obviously the scale is going to be small, right? But using, for example, something like a GPT-4 and saying, oh, this is what this agent did, and just tell me according to the goal, just give me a score or something, and then so basically to be able to automate that process. Have you considered this approach?
Yeah, thanks. That's actually a very, very good question. So basically, this has been considered. So basically, because ChatGPT it has used a lot of human data to train that, so it has common sense knowledge. So basically, but we could ask it to label to generate labels. So and there are like some works I remember there like some papers mentioned that GPT-4 can be better than human labelers. I think it's on. In some NLP tasks, but for the reinforcement learning side, I think this kind of brought to my attention, but I haven't tried that yet. But actually, I think the problem, the research question here would be that GPT-4 can generate feedbacks in a more efficient way, but it could be less accurate than human labelers. So basically, it's like the problem of trade-off for the efficiency and the label noise. So yes, thanks.
Thanks very much for that question. Before we break, I think we just got one quick question from me, which is that how challenging do you think this stuff will be to pick up for game developers? So there's like game developers in the audience who maybe are thinking about these new technologies, but how challenging would it be to kind of learn this from scratch, do you think, for them and put it in a game?
Put it in game? Well, actually, I think that So actually, this kind of things, because I think many developers are still already started trying to using AI. So basically it's kind of a little bit learning curve, not very steep, a little bit mild learning curve.
I guess if anyone does want to ask you, they can kind of find you at one of the coffee breaks today and maybe work with you in the future.
Yeah, and also mention that the live demo has already been set up in the arcade exhibition area. So basically, if you want to play with our AI agent in Overcooked, so you can go there and play. It's just at the corner of arcade. It's already set up, so try it out.